cruising like cargo ships. Now we enter the molecular jungle. Look, at this scale, everything is constantly jiggling, twisting, and vibrating. This is not a static world. It is a violent, chaotic dance floor. Wait, think about the speed of that jiggle. Those molecules are slamming into each other billions of times every single microsecond. It is a hyperactive playground. And yet, despite all this frantic chaos, the structure remains perfectly intact. It doesn't dissolve. It holds its shape beautifully. You see massive proteins looking like tangled balls of yarn folded together. And weaving between them are trillions of water molecules. Each water molecule is made of 2 tiny hydrogen atoms hugging 1 oxygen atom. They are packed together like commuters in a subway car at rush hour. Here's the part nobody tells you. At this level, gravity does not matter. Gravity is a weakling. Instead, electromagnetic forces rule everything with an iron fist. They pull, push, and snap atoms into tight, structured grids. This intense packing is why so many atoms can sit in your palm. If we zoomed in until a single atom was the size of a marble, your hand would stretch from the Earth all the way to the moon. Yet in reality, it fits neatly in your pocket. This is the magic of the quantum scale. It is a universe built on packing efficiency. But how do we write out a number as big as the atoms in your hand? How do we even begin to visualize a number like 10 septillion? People say 1,000,000 is big, but that's just a tiny drop in the bucket. To truly understand why your hand beats the cosmos, we have to look at the math of big numbers. And trust me, this is where your intuition fails. Because when we write out this scale, the zeros start to play tricks on us. Let that sink in for a second. If you counted every atom in your hand one by one at a rate of 1 per second, how long do you think it would take you? The answer is beautifully simple, yet completely terrifying. It stretches far beyond the age of the universe itself. How is that possible? Let's think about counting to understand this massive gap. If you counted out loud 1, 2, 3 at 1 count per second. To count to 1,000,000, it takes you about 12 days of nonstop counting. To count to 1,000,000,000, it takes you 32 years. Now, think of someone you know who is middle-aged. They haven't even lived 1,000,000,000 seconds yet. But we aren't talking about 1,000,000,000. 1,000,000,000 is just 10^9. We are talking about 10^25. That is 10 septillion. Written out, it looks like a 1 followed by 25 terrifying zeros. If you counted 1 atom in your hand every single second, it would take you about 300,000 billion years. Stop. Let that sink in. The universe itself is only 13.8 billion years old. The age of the universe is a tiny drop in the bucket compared to the time it would take to count the atoms in your palm. Now watch what this implies. If you think that's big, watch this. Let's take all the stars in the observable universe. That number is 10^24. That is 1 septillion stars. It means there are 10 times more atoms in your hand than stars in the sky. For every single star in the night sky, in every galaxy we can see, you have 10 atoms in your hand. Try this. Hold your hand near your face. Imagine 10 full galaxies, complete with swirling dust and billions of burning suns floating right above your palm. Each galaxy has billions of stars, and you can cover all of them with your thumb. But why? How can a universe which is so unbelievably massive be so poor in stars? The answer is beautifully simple, and it has to do with how nature builds things. You see, nature is incredibly lazy when it builds the cosmos, but highly efficient when it builds you. When we look at a star, we think of it as a massive solid object. But there is a catch. That sounds impossible until you see the trick. Let's look at the true scale of a star. Look at the sun. It seems solid, like a giant burning rock hanging in space. But that is an illusion. A star is not solid. It is a giant chaotic ball of hot gas and screaming plasma. And compared to your hand, it is incredibly bloated. Here is the part nobody tells you. Stars are mostly empty fluff. If we look at the average density of the Sun, it is surprisingly low. It is only slightly denser than water. And other stars like red supergiants are even more ridiculous. Take Betelgeuse, the massive red star in the shoulder of Orion. If you placed Betelgeuse in our solar system, it would swallow Mercury, Venus, Earth, Mars, and even Jupiter. It is colossal. Yet, its density is nearly 1,000,000 times lower than the air you are breathing right now. It is essentially a glowing, hot vacuum. A red supergiant is a cosmic ghost, stretched thin across the dark. This is where your intuition fails. We see bigness and assume complexity. We see scale and assume density. Wrong. The universe is terrible at packing matter. It stretches its atoms across light years of emptiness, letting them drift alone in the dark. Your hand, however, does the opposite. It pulls atoms together into a dense, tightly locked liquid and solid matrix. Your skin, bone, and blood have a high density because they are held by the strong bonds of chemistry. If you took the matter from a giant star and packed it as tightly as the atoms in your hand, that giant star would shrink to a fraction of its size. Now watch what this implies. The stars are scattered across the universe like a few lonely light bulbs in an empty stadium. If we averaged out all the matter in the universe, it would be shockingly thin. How thin? The cosmic density of the universe is almost impossibly close to zero. But why is the universe so bad at packing things together? Why did it leave so much empty space between the stars? Let's look at the cosmic density lie. Let's face a cold, hard fact about the cosmos. People say the universe is crowded with galaxies, but that is just a lie of perspective. If we took all the matter in the entire observable universe, every single star, planet, black hole, cloud of dust, and stray atom, and we spread it out evenly across all of space, what would the density look like? It would be roughly 1 hydrogen atom per cubic meter. Think about that. Imagine a box that is 3 feet wide, 3 feet tall, and 3 feet deep. In that massive box of space, there would be exactly 1 lonely atom. Now look at your hand again. Inside your hand, there are more than 1025 atoms. They are packed into a volume of just a few cubic inches. To get that many